So why do we care about groups? Groups are pretty useful mathematically because they're very simple objects overall. I know that doesn't seem like that sometimes, but their properties apply to a whole bunch of different things, and we can use those properties once we know something is a group to learn all sorts of interesting new things about it. And it sort of shortcuts a whole bunch of mathematics for us. I'm going to give you a very basic example of that right now. So, using group properties, first we have to remember what our group properties actually are. Ricka! First off, associativity. And I'm going to try and give them in the same order each time, but I make mistakes. It happens. Then we need identity elements for every every operation that makes the thing a group. And last but not least, we need inverses for every element under that operation. All good. So, the benefit of classifying something as a group as a group is that all the conclusions we draw from groups in general from groups in general then apply to the object we classified. This is actually a really basic mathematical technique. And it's one of the things that sort of sets math aside as a section of human knowledge. It's one of the great advantages that we have in mathematics. There's still huge issues with this. So classification, for example, in mathematics can make it so that two identical objects approached from very different sections of math are not recognized as identical for quite long periods of time. This leads to sort of staggered growth. There's also a big advantage in sort of hiding that a particular object is really another object. If you're trying to prove something new for a particular class of object, you don't want to reveal where you got your stuff from. The overall effects on this on mathematical knowledge, however, are generally positive. So, what is that general technique? That basic technique. Let's say we have an object here, and we start getting really good at proving things about it. You know, we got proof over here, we prove that it's happy. We got a proof over here, we prove that it's round. We get a proof over here, we prove that it's got a smiley face on it. Proof over here, we prove that it's got eyes. All of these other properties of this object, etc., etc. And we start to build up a literature, a whole section of knowledge all about the different proofs for this particular object. It's all very exciting. So, you manage to prove things for a particular object, in this case, this happy little guy right here. So, then the actual technique comes into play. Proving things has its own set of techniques and stuff, which we're not really talking about right now. But then the actual technique comes into play. If we can show that a new object, for example, this guy, ooh, similar but different. Oh, madness. Similar but different. If we can show that a new object is actually the same as our old object, under some transformation, in this case, It's just a rotation, right? So make sure I'm drawing my smiley faces correctly. If I rotate my smiley face around, hey, congratulations, we can see it's the same thing. Then, all the old proofs proofs 1 through n apply to our old object. Now, the wise of you may be noticing that a transformation has occurred, and there is a slight asterisk on this technique. We have to be aware of the fact that we performed a transformation, and sometimes our transformation can matter in terms of the proof. So in reality, what's happening is we're proving a whole bunch of things for this object, we're flipping it over, we're going, okay, what really happens if I then use all these proofs and then I flip my piece back over? So there's one final missing step there. But that's obviously a lot easier than having to go through and prove each of these things sequentially, again, for an object especially like this one that is really very similar. So, the more examples of the object we can find, the more examples of the object we can find, the more work we save on proofs. And you may be like, well, I don't care about math. I don't care about proving things. This is also very useful for computer programming. Ooh, because all of a sudden, if we're recognizing similarities between objects when we're programming, we're able to reuse substantial sections of code, especially if we're coding according to good principles. We can reuse sections of code we can reuse sections of code in order to draw conclusions. We can reuse sections of code in order to write programs that are more powerful and faster than we could otherwise. So, groups are everywhere. Understanding them is a big help. Got there.